Okay, so if we think about EMR and light as a particle, and if we think about, like with our whole photoelectric effect, there's almost like we think about the photon colliding with an electron. So if there's collisions happening, there must be momentum, okay? Because when we were talking about momentum, we looked at collisions quite a bit. That was basically what we are focused on. So if photons are particles, they should have some momentum, even though it's really small. Since the momentum of a photon would be very small, it was challenging to design an experiment to measure this very small momentum. Also, EMR has no resting mass, so the classical method for calculating momentum, where we go P is equal to m times v, could not be used. The new formula was derived to calculate the momentum of a photon. So this is our formula where we have P is equal to h over lambda. Now, keep in mind this is just momentum of a photon, so any EMR, but an electron, okay, we still use P is equal to m times v. Okay, so this is for photons. That means that of EMR, electrons are not EMR. Okay? They have a specific mass, 9.11 times 10 to the negative 31. Okay? So, now here's something very, very important. For these formulas, you must use the H that has joules in it. Super, super important to remember that. And the reason is because in order for our units to cancel out, we need that joules, not the EV. Okay? Now, if you're kind of trying to make it, I know some of you are trying to make rules for yourself on which H's to use and when and stuff like that. Think like with these formulas, it doesn't have an H and an E in it, so you can't cancel out the EV anywhere. You need to use those joules for the units to work out with momentum. Okay? Again, a formula for momentum which supports the particle theory still contains some ideas from waves. Clearly, this is a wave type theory, wavelength. It's that EMR has waves. So this continues to support the idea of the particle wave duality. Which principle is that? Number 9. EMR acts as both a wave and a particle simultaneously. So we're seeing this kind of more evidence for supporting that we can't just use one or the other to explain it. We need both. So a guy named Compton performed an experiment to show that photons have momentum. He directed a beam of X-rays at a thin metal foil, similar to the photoelectric effect, but the X-rays have higher energy, and that's the, like, you had to use something higher than just white light for this experiment to work. Compton still observed electrons being emitted from the surface, but also found that the X-rays scattered after hitting the target. The scattered X-ray had a change in direction, so it actually moved which direction it was going, and an increase in wavelength. this means, so if it increases in wavelength, that means it's decreasing in energy, right? The larger the wavelength, the less energy. So this means that the scattered photons within the X-rays had less energy and less momentum than the incident photons. So there's an actual, we think about it kind of like as a collision. Similar to the photoelectric effect, the conservation of energy, what principal number is that? Five, yes. So this conservation of energy principle can be used to explain Compton's observations. So when we think about it, we can say our energy in needs to equal energy out. So we'll say our E incident of the X-ray is equal to E scattered X-ray plus EK of the electron. Now, a note here is that the work function is so small compared to the other energies, it is simply ignored. So for these formulas, you don't use W, okay? Because it's such a high energy incident coming in compared to how much work it's needed. It's negligible. It still exists, it's just not significant enough to include. Compton's experiment is simply a collision between an electron and a photon. Therefore, the conservation of momentum. What principal number is that one? 4, yes. Can also be used to explain the Compton effect. So again, if you are going through kind of a question where you have to make these assumptions and then it asks you what principle did you use, you would say number 4 if you had to use this assumption. So our assumption then is that the sum of the momentum, P means momentum, before is equal to the sum of the momentum after. So if we put that into context, it's the momentum of the incident photon because we assume that the electron is at rest because it's in metal, like it's just in a metal piece of metal, so it's not moving, okay? Or it's just vibrating so minimally it's not moving. So all of our momentum is incoming incident photon, and then we have our scattered photon plus our scattered electron momentum. So this will be kind of good because it's like going back to Unit 1 and kind of reviewing some of that momentum stuff without, having to do it all over again. So assumption now. Collisions need to be what at the molecular level? We talked about this assumption way back when. It's a subatomic particle, yes. What did we have to assume about subatomic particle collisions? When they hit so like when we have like say two cars crash, there's energy loss due to friction, and so that's an inelastic collision. But subatomic particles are so small that when they hit and they bounce off, what can we say about those? They're elastic, yeah. So we talked about inelastic and elastic collisions, and that was kind of an assumption we made before, was that when we dealt with big stuff, that it was always inelastic. And I told you, okay, subatomic is elastic, but now we're actually going to use that, okay? So the conservation of momentum strongly supports the particle model of EMR. Now, I want us to think about one thing for a moment. Momentum, P, is that a scalar or a vector quantity? It's a vector quantity because it involves velocity, right? P is equal to m times v, or like when it's not a photon. But in its nature, it is a vector quantity. So this is really important for your questions. You can only use this assumption when directions are provided. So if it tells you like the incident photon is traveling east and the scattered electron goes north, right? Because you need to actually, with momentum, since it's a vector quantity, you have to like convert the north into positive and the west into negative. Things like that make your x and your y coordinates. If you're not given directions, you can't use this because it's not possible if you don't know which direction it's going. So for the one before that, the conservation of energy, that is energy what? Scalar or vector? Energy. Scalar. Energy in its nature is scalar. It's just like how much energy does something possess. So when we think about this being scalar, if you are given directions or if you are not given directions, you can always use this one. Okay? You can use if no directions, but it should also work if you are given directions as well, if you look at the energy. It's just that momentum should be left for direction questions. So just keep in mind that information that you know about momentum and apply it to this stuff. So when we think about, say, an X-ray photon coming in, if it's incident, it's coming in, it would have a shorter wavelength than what is leaving, so the scattered one would have a longer wavelength. So a shorter one would mean that it had more energy, and a longer wavelength would mean that it would have less energy. Because keep in mind the speed is still the same, right? It's still 3 times 10 to the 8 meters per second. The only time when speed changes is when it goes into a different medium, right? And that's when we had something different happening with wavelength because frequency stayed the same when it goes into a different medium. Okay, where are these formulas found on your data sheet? What heading can we see these formulas that we've talked about so far and the one that's coming up here? What black box heading are they under? Which one? Look at your data sheet. Which one? I would agree with Kim. This is under the quantum mechanics and the ones that we're going to be talking about next too. So here is where we're going to be focusing our energy today. So the formula that describes the Compton effect is described as such. So the lambda is the change in wavelength, or the delta lambda. So it's how much it changed between the shorter to the longer one. Planck's constant, again, needs to be the one that uses joules. Very important. Again, it has to do with the units and canceling things out. Mass is our mass of the electron. Okay, really important. C is the speed of light because it's not going through a medium, a different medium other than air or vacuum. So we leave it always as that constant. And theta is the angle between the initial and final wavelength. So here it would be theta. How much it changed its direction. There is also an equation that relates the energy of a photon to its momentum, where we have E is equal to P times C, so the energy of a photon is equivalent to its momentum times by the speed of light. So this is kind of what we have to set up with for all of our information.